Hello, welcome to the class, student. Today we will continue with the IUPAC system of nomenclature of coordination compound. So when we do nomenclature of coordination compounds, and we will do IUPAC system. You are familiar with this term, and when we say nomenclature, it means what? The two things we have to do in this, that is, you will have to learn to write the name of the compound whose formula is given, and secondly, the name will be given. You should know to write the formula. So first we will do writing the name. So writing the names, for that some important rules are there that you have to remember. The first thing, as you know, a complex compound, a coordination compound, consists of two parts. One is ionosphere and the other part is a complex entity. Complex entity. This is one thing, and this is, you can say, the first example. When ionosphere is before complex entity, the example you have done, K4 FeCN6. This is ionosphere and this is complex entity you have already done. So when we have this compound, such compound, and you know that a compound will be having a positive part and a negative part. When positive part is ionosphere and the negative part is complex entity, then complex entity is anionic entity. So in this case, you will have to first write name of this metal which is present in ionosphere, and that is your potassium. That has to be in a small letter, not capital letter at all. Potassium is for this. You have not to write any prefix for the number of times potassium atom is used here. So here simply the name of the metal which is constituting ionosphere has to be written down with a small letter. Even the first letter will also be the small letter. And so this is your ionosphere part is done. Then you will start your complex entity. Now here, if you just look for this, and if I write the structure of this, that is 4 potassium ion and 1 complex ion, this part. So this is ionosphere you have named first, as I told, potassium, and this is your complex entity you will be naming as a whole after this. So this is anionic, 4 negative charges. So when we write the name of the complex compound, first we write positive part, then we write the negative part. If example is this. Now take another example. As we have taken the second example earlier, copper NH3 whole 4 SO4. In this case, this is complex entity. If you write the ionic structure, 2 positive and sulfate 2 negative. So this is ionosphere, which is here ionosphere, and this is complex entity. So this is complex entity, Their complex entirety is positive. So it is cationic complex ion, and this is ionosphere. In this case, you will have to write name of first the complex part, and then you will have to write the name of the ion. Every letter which you will be using to write this part will be small and will be as one single word, no space. Even if you write name of this and name of this, ammonia, which is called amine, and this is copper, without any space, all letters small. And when this name will be over of this part, then this little space, then you will write sulfate. So positive part first and then the negative part. And the third, if you just see a neutral complex, like you have done nickel carbonyl, this is having no charge, this is as a whole, so this will be written as a whole, so there is no question arising of positive or negative charge. So this is first thing you have to keep in mind. So you have to write first positive part of the salt compound, and then you have to write the negative part. So positive part may be ionic sphere or a complex sphere, and the same is with the negative part. Now the second thing is about ligand. Ligands, you know, are the atoms or the group of atoms which are attached to the central metal atom and is written in the square bracket. So these ligands you have to learn. Last time we have done in detail. So what is that ligand? Various kinds, you know, monodentate, didentate, that all example I have given to you. So you have to learn them. So in monodentate, you have one example of ambidentate. Ambidentate, this part we had not done at that time in your classification, but you remember ambidentate. Ambidentate means it is monodentate. It is having only one point of attachment at a time, but the atoms through which attachment will be taking place, that may be different depending upon. The example is CNS, and this is your thiocyanate, and this is NCS. This is your isothiocyanate. So in this case, the bond will be through S, and in this case the bond will be through N. The central metal atom will be attached to S, the central atom will be attached to N. So in this case the bond will be like this, S, N, C, and in this case the bond will be like this. So when you will name here, it will be your, and you know that when we write ligand, we don't end the name with E. The E will be replaced by O, so cyanato. So for this, the name will be thiocyanato S with a hyphen, and then in this case the name will be thiocyanate N. This way also you can write, but it is having a special name, isothiocyanate, so you can write in place of this whole thing, isothiocyanate. So this is having two names, the other is isothiocyanate. So any one of the two you can write, but this is preferred over this. Now another example of ambidentate. Ambidentate ligand is monodentate, which has only one point of attachment at a time, but the atom through which it is going to be linked, the non-metal through which it is going to be linked to the central metal atom, that will be different. So other example, you know that NO2 and ONO. This is nitro group, a small letter, ligands always with a small letter nitro, and this is nitrito. nitrito, nitro and nitrito. So this you will have to write, when you write the name, you can simply leave nitro or you can write nitro N. Then here you can write either simply nitrito or but either you can't write nitro. You will have to write nitro N, and here nitrito you write, or nitrito you are writing it, it is understood that the bond is through oxygen. But if you are writing it as nitro, then you will have to write with hyphen NO that the suffix, the atom symbol which you are writing, that should be capital, and the name to name, these two things will be separated by a hyphen. So remember that in your book, I have seen that nitro, this NO2 is given and the name is used nitrito. So it is mistake, printing mistake, so be careful when you read example from the book. This is the second example of ambidentate, which is quite often given, and the third is cyanide, that is cyanido, and isocyanido, cyanido or isocyanido. So if you write it cyanido, C cap small, cyanido. So here bond is with the carbon, and here it is cyanido N, or simply you write it I small, isocyanide. So when you write iso, it is understood the bond is through nitrogen. So this is some precaution you have to take when you write down the name. So this is one thing about ligand. The second thing about ligand, that when a ligand is used or is present more than once, so if it is your like monodentate, chloro, bromo, ido, and these all, or acetato, oxalato, where the name of the ligand is not containing any this letter di or tri or tetra, when this is not present in the name, like oxalato, acetato, oxo, cyanido. So if these are, like, you take example, if you have suppose CO, or I write this example Fe, which you have already done, CN6. So this is your here ligand. It is used 6 times. So you will have to write the name of this cyanido. That is true, but the cyanido, how many times this is 6 times. So you will write here hex, Hex, hex without any space, is with a small letter. Hex cyanide or hexacyanide, rather hexacyanide. Okay, and if it is Cl, suppose it is Cl 2 times, so it is dichlorido. If it is 3 times, suppose it is your NH3 is used 3 times or 4 times, so tetramine. So ligands which do not have the term di or tri in their names, then we use the prefix di, tri, tetra for the number of times they have been present. They are present. So now here, this was the first example. The second example you take, if you have a ligand like En. What En we have done? En is ethylene diamine. This is En, a ligand. Like you can take CuEn twice and SO4. This is a compound. So here ligand is En and En is used 2 times. As you see the name, in the name itself the term di is there. So you cannot use here diethylene diamine. Instead of that, it is 2 times, so you will be using for 2, you will be using bis, for 3 you will be using tris, and for this tetrakis and takis and so on. So here the name for this, the name will be your bis, no hyphen, and in the bracket will be the name of this ethylene diamine. So remember that. Okay, so this is for this En. Okay, that's En is a big name for ligands. It has to be written in the small bracket, but there shall be no hyphen. This was the second example for the ligand, when a single ligand is used more than once in the compound. The third example, if it is methylamine. If methylamine, ethylamine, this is used as a ligand, although you will be going across not such ligand, but still if you go across, so this M will be small methyl. Then we are not using for this, we are not using di if it is 2 times. If it is 2 times, you will not use di. If it is 3 times, you will not use tri, and so on. Because if you write dimethyl here, it means methyl is 2 times, so there will be a confusion. And so when it is dimethyl is 2 times as a ligand, so you will be using again here bis. So for this it will be bis. And if it is 3 times your methyl, bis for 2. And if it is 3 times, it is this exactly same. And so on. So it will be bis methyl. As I told, when you write bis or tris, there will be no hyphen. And the name of the ligand will be in the small bracket and without any space. Now, so this was the second rule. Now the third rule, you have to write the names of the ligand. So take an example, suppose cobalt, and it is linked to a ligand chlorine and linked to cyanide and NO2 and NH3. Suppose this is your complex compound. Okay. Now, if you have to name, I am just going to teach how you write. If you have more than one type of ligand, then how you have to name it. I am telling you how you have to name it. So, how you will be naming it as, that is, this is your chloro, you know. This is cyano or cyanido. This is nitro, and this is amine. So you will have to write their names, ligand name, how? Alphabetically. The first letter of their main name. So here we have first amine, but amine is 3, triamine. So this prefixes which will be there with ligand, they will not be taken into account to give the alphabetical order. So you will not consider T of the tri, only you will look for the first letter of his name. So A will come first. So first it will be amine, and after that the C, this we have two ligand starting with C, but alphabetically this will come first. So next will be chloro without any space, chloro, then it is cyanido, and at last it will be nitro. So this way, and here amine is your 3, so you can write here tri. without hyphen and any space. So this will be the way to write the name of the ligand. Okay. Now the fourth thing. Naming the central metal atom or ion. So for this you will have to see the complex entity. Complex entity is of three types, you know. First is, if it is cationic, or it is neutral, or it is anionic. I give you the example of cationic. Cationic we have done copper, NH3, whole 4 and 2 positive. This is cationic complex entity. Example for neutral, it will be FeCN6. Sorry, this is for anionic. CN6 and 4 minus, and for neutral, NiCO4. So you have to identify the complex. This complex we had written like this, SO4. So in this you have to identify what is the charge on it. So that here, if you know sulfate is having negative charge, so here on this there will be the positive charge. 2 is the valency of sulfate, so yeah. Then here the name was K4FeCN6, so this is positive part. So potassium, and this potassium valency is +1. So this valency will be 4, and since it is an anionic part, so there will be 4 negative charge. So this is anionic and this has no charge. So when we have cationic or neutral complex entity, then the name of the metal is written as it is, no change. And that will be written after writing the names of all the ligands, as we have seen in the previous case. Ligand name you will write alphabetically, and when all ligand name will be over, without any space, with a small letter, you will write the name of the metal. In this case, we will have tetraamine. Are you noticing, student? Last time in my class, while I was teaching you these all names, so I told you here tetra, double A and double M. Okay, no grammar rule you have to apply. There are 2 vowels. If they are joining together, then first vowel will be omitted. Not that rule has to be followed. So it is tetraamine, and the name will be what? This is now no more ligand, so here it will be copper. So copper you will write as it is, and with its oxidation number in the small bracket. What is the oxidation number? You can calculate. This is X plus 0 plus 2. So this is 2. So X is equal to 2. So oxidation number of copper is 2. So you will write with a Roman number, capital Roman number. With that you will write oxidation state in the small bracket. Now, for neutral if I take nickel CO4, it will be tetracarbonyl. No space so there, but you will leave no space, nickel, and its oxidation state. This is a neutral ligand having no charge. So this is X plus 0 is equal to no charge, neither plus nor minus. So X will be equal to 0. So here oxidation state is 0. So for cationic and neutral, the name of the metal is written as it is, no change. But for anionic complex entity, you have to be careful. anionic entirety and complex entirety. Example, we have FeCN6 4 minus. So what it will be? Hexacyanide, the name of the ligand. Then we have iron. Here you will have to use its Latin name, that is ferrum, but the name will be ending with ATE. That you have to remember. When complex entirety is anionic, the name of the metal will be ending with ATE, and for that you will have to use its Latin name, where we are using Latin name for the metals. So if it is nickel, for nickel there is no Latin name, it will remain nickelate if it is Ni here. But if it is copper, it will be cuprate. If it is iron, it will be ferrate. So it will be ferrate. Ferrate, ferrate. Okay. And this ferrate, and since here we have K4, no charge, so there will be potassium in the beginning, no doubt. And this is ferrate. And then its oxidation state. So what is the oxidation state of this? If you calculate with this negative charge, it is convenient. We can do iron X plus minus 1 into 6 is equal to minus 4. So minus 6 goes there, so it will be plus 6 minus 4 is 2, so oxidation state is 2. So here potassium hexacyanide. If it is potassium here, then no charge. So you will write potassium. That part we have done earlier. And when this is not there, you have 4 negative charges. Then you will write after this a word ion also. Leave some space and write ion if a charge is there. If it is your Cu NH3 whole 4 sulfate. So what you will write? Tetra amine. Since this is positive, so name will remain as it is. Copper, what is the charge that we have seen? 2. And this part, leave some space, and then it will be sulfate. Okay. And if this is not there, you have 2 positives, so you will not write sulfate. Instead, you will write ion. Leave space and write down ion. So what have you to remember? For cationic complex entirety, the name of the metal remains as it is. For neutral, the name remains as it is. But for anionic complex entirety, the name of the central metal atom is ending with ATE, and then after central metal atom, you have to write in parenthesis with Roman number the oxidation state that you will have to calculate of the central metal atom in this particular complex compound. A central metal atom can have more than one oxidation state in normal, but which oxidation state it is present in this complex, that you will have to calculate. So this was here, and now see the name. If our naming the complex or cationic and anionic complex entirety in a complex compound. In one complex compound, you have both, there is no ionosphere, you have both part as complex. Take example, say copper, one example I have written and brought for you, very common as in board, that is cobalt, Cl2, NH3, pole 4, and chromium I think with cyanide, CN6. So here and here it was thrice. So this is first part. So this is cationic part and this is anionic part. How you can know that? You can write very easily. It's ionic form. Cobalt, Cl2, NH3. Need not to write in examination. You can directly understand, you can do. But for your convenience, I am doing it here separately. And so here we will have 3 molecules of this. Okay. This is 3 means the valency of this part is 3 and valency of this part is 1. So plus 1. And we have this part Cr, CN6. This is having negative charge. And how much negative charge? The valency of this will be 3. So 3 minus simple valency rules which you have done for normal salt. So this part we have as a cationic complex entity and this part we have got anionic complex entity. So after this, even directly here you can decide, you can do that work what I have done mentally also. So name. So first we have to write name of the positive part, then of the negative part. Same rule. So here we have this as chloro, this as amine. So amine starting with A. So first we will have amine. It is tetra. So we will start with tetra. Tetraamine. Then it is dichlorido or chloro. This is. Then we will have cobalt, and for this you will calculate oxidation state. It will be convenient from here to calculate oxidation state. This is X. This is minus 1 into 2. And this is your 0, neutral, into 4 is 0. And this will be is equal to 1. Plus 1 means 1. So what it will be? Minus 2. Minus 2 will go that side, plus 2 and 1 will be 3. So cobalt oxidation state is 3. So this part is done. I repeat it. Tetraamine, dichloro or chlorido, cobalt, since it is positive cationic species, so name of cobalt will remain as it is. It will not be ending with ATE, and in the parenthesis you will write is oxidation state. Oxidation state calculation I have taught you in detail. So yeah, if you know the chart through the formula, you can calculate the oxidation state. This is X. Minus 1 is for chloro group, chlorido. Minus 1, 2 atom. This is 0 into 4. And this is charge, net charge is positive. So this is 1. So it will be minus 2 will go that side, plus 2 and 1 is 3. Now you will start this part without any space. You will start with this part. So it will be hexa. It has to be in one line. Cyanido. This is anionic part. So it will be chromate. And you will calculate as oxidation state. What is the oxidation state here? Minus 1 into 6, or just you can look here, then you can find out. And this is X plus minus 1 into 6 is equal to minus 3. So it will be 6. Minus 6 will go that side, plus 6 minus 3 is 3. So oxidation state will be 3. Since it is a salt, main it is given the salt, no charges with that. So here it is your tetraamine dichloro cobalt 3 hexacyanidochromate 3, the name. Okay. So this is the case you have seen here. Remember, what is the case? I want to draw your attention on this. Cl2, NH3, 4, and thrice, and here chromium, and Cn, and 6. Here you can very easily know what is the valency of this part and what is the valency of this part. First part is always cationic and this is anionic. So you could very easily write the valency, you could know. And if you know the valency of these part, you can very easily find out the oxidation state. But if you have an example, another example I give to you, which I have brought for you, that is platinum PT Cl2 NH3 4. This and PTCl4. See, in this case you see no number is given here, no number is given here, but it does not mean that valency of this is 1 and valency of this is also 1, and on exchange it is the same. It could be valency of this is 2, this is 2. It could be the valency of this is 3, this is 3. So if valencies are different, oxidation state will also be different. And so you will have to find out first what will be its oxidation state. So I will teach you to find out oxidation state. So for that you will have to learn what are the oxidation states of these metals. When you study D block elements in detail, configuration part you have done in 11, through configuration you can very easily know how many electrons an atom can lose, and then according to that you will have its valency. Like for copper you have done in class 11. This is the configuration for copper. Actual configuration I am writing 3D10 and 4S1. It is not 3D9, 4S2 actual. That was expected. Okay. So actually in this case it will lose 1 electron. If this loses 1 electron, so here will be 1 positive charge. It can lose 1 more, so it will be 9. So in that case we will have plus 2 charges. So copper valency can be plus 1 or copper valency can be plus 2 depending upon the outer electrons, how many outer electrons it is losing. So this part is depending upon the configuration, and that you can do in detail in D block element, or it is based totally on the oxidation, on the configuration of the atom, central metal atom. So there are several oxidation states for a particular metal, but all oxidation states are not very active or is always considered. So what is very common oxidation state, that is only taken into account. So for platinum, the oxidation states which are very common are 2, that is plus 2 and plus 4. So you don't know which oxidation state, because when you write the name, when I will write the name for this, look here what it will be. For this is positive part, that is negative part. First part is positive, second part is negative. So what will be the name? Tetraamine dichlorido or chloro. Positive part, so it is platinum, and in the bracket you will have to write its oxidation. So now if you cannot calculate its oxidation state because you don't know what is the charge here. It may be 1, it may be 2, you don't know, because from the formula it's not clear. In such cases you will have to consider platinum's both oxidation state and you will apply. So how to that is, so if you take platinum is 2, to find out the charge on the complex entirety, what you will have, so charge formula is there, charge on complex entirety is equal to oxidation state of the central metal atom or ion plus total charges of ligands. This is here. Whatever you get, if you know the oxidation state and this, then you can very easily establish the charge. Okay. So how to do that? This I show you. So this formula we will be making use. So I'll take up for this part PtCl2 NH3 whole 4, and I have to know what charge we can put over here. So platinum first I take, if it is plus 2, then this will be minus 1 into 2 plus this is 0 into 4 is equal to what? This will be your minus 2, okay, minus 2, this is plus 2 minus 2 is equal to this, to cancel it is 0. So it means here charge will come 0, that is not possible, because according to the formula here it has to be the plus charge. So in this case platinum oxidation state cannot be true. Is this clear? So the 0 is not possible. Now we will do with 4. If we take here 4, what we will have? Plus 4 minus 2 will be your 2. And so net charge is left over 2, plus 2 is left over the next. So here the charge will be 2 plus. And we know that here we have a positive charge because it is first part, first complex entirety. So here the charge will be 2 plus. So this is for this particular case. In this case, so what you can write, if I just write for this, the ionic form PtCl2 NH3 whole 4, and you can write here 2 plus. Okay, and then I will write for this PtCl4. What will be the charge that we will do now? So now I will calculate for this part PtCl4, the charge. Platinum could be 2 plus 2 plus minus 1 into 4 is equal to what? Minus 4 plus 2 is plus 2. So the net charge will be here plus 2. Okay. And if I take 4 here, plus 4 minus 1 into 4 is equal to, so minus 4 and plus 4 will be 0, and so here we will have 0. And this has to be negative, cannot be 0, so this is not possible, this is possible, so here will be 2 plus. So both are having valency plus 2, both. Cationic is having plus 2, anionic is having plus 2, and that's why no number is given. So when this is plus 2, so what is there? This is plus 2 if you have taken, so platinum oxidation state was what? 4. Now look here, or 2. When we have taken here, we have calculated just now. That is here, if we take PtCl2 NH3 whole 4, now we have got this. So we can calculate x minus 1 into 2 plus 0 into 4 is equal to plus 2. So plus minus 2 will go that side, so it will become 4. So here oxidation state is 4. And this part is done. Now we will come to this part. So what will be this part name? Without any space, you will start with tetra chloro platinate, because it is an anionic part. This is, and in this case we have seen the oxidation state is 2. The charge was -2, and so you have seen here it was 2. Okay, and so this is the name. I hope it is clear. One more example I give to you. So can you see the difference in this example? In this you had the number given, and so you could know very easily what is the valency. So you could find out the oxidation number. In this case no number is given here, so you could not say it is 1, it is 1 or 2 or 2. So for that you will have to consider different common oxidation states of the central metal atom, and you will have to calculate its oxidation number according to the position, whether it is present in cationic part or it is present in the anionic. One more example I give you of this kind, that is I have brought for you, that is chromium NH3 whole 6 and cobalt CN whole 6. Again see, no number. So chromium common oxidation state is +1 and +3, and cobalt oxidation state is +2 and +3. Okay, now so for this we will find out what is the charge here. So what it will be for Cr NH3 whole 6, if you have to find out the charge, first we will do with +1. So +1 plus 0 into 6 is equal to what it will be? +1. So here it is +1 charge. Okay, this is cationic part and can have a valency plus. Okay, now with 3 we will do, if we take 3 plus 0 into 6 is equal to, so it will be 3 and not 0, the net charge will be +3. So 3 plus. So either it will be +1 and this is any one of the two it could be. And now we will calculate for this cobalt. Anyone, still we are not sure which it will be unless we don't calculate for that. So both are plus, so it could be this or this. So out of the two, which one will be, whether oxidation state will be this or this, that will be depending upon this. So we will be calculating for this CN6 plus 2 plus -1 into 6. So it will be +2 -6. Net charge is your -4. So here the charge is coming 4 minus, or with 3 we will calculate. With 3 what it will be, if we take 3 plus 3 -1 into 6 plus 3 minus 6 is equal to -3. Okay, so this is -3, so here 3 minus. If we take 4 and this is, so here it should be 4. If this is 4, here it should be 4. Okay, and if but here no number, it means both numbers are same. So +3 and 3 minus is taken. So here chromium oxidation state is 3 and cobalt oxidation state is also 3. So you have calculated. I hope this is clear. You can again and again see this video and you can know the process. So what will be the name? hexaamine chromium 3. Then hexa cyanido cobaltate 3. This will be okay. So you will take practice, student, and you will do it. Now the second part is writing the formula. If the name is given, you have to write down the formula. So like you have potassium hexa cyanido ferrate 2. If this is given and you have to write the formula, so you can decide very easily what is ionic sphere, what is positive part, what is negative. So here two metals you have. So out of the two you decide which is central. Central metal atom is always written after ligand. So this is complex entity and this is ionic. So potassium K and hexacyanido, it means Cn is 6. Central metal atom is always written first in the square bracket. So you will write this in the square bracket. First you will write the central metal atom Fe in the square bracket. We have no other ligand, so Cn6. Okay. Now you should know that what is the charge on it. So the charge calculation I have told you already. That is oxidation state of this is iron oxidation state is +2 and +3. So which one out of the two it will be, you can decide. That is what iron is if you take here Fe Cn6. Now what charge you will put here? Fe, if you take +2 plus 1 into -6, so it -6 that is your 4. Okay, so difference is 4 minus 4, so here you will have 4 negative. If you start with 3, it will be -3, 3 minus. Okay, and potassium valency is what? Potassium valency is 1. So potassium valency is 1, so this is 1. So here either it could be K4 FeCN6 or it could be K3 FeCN6. Both are correct. Potassium ferrocyanide and potassium ferricyanide, K4 and K3. Okay, so that is the way how you have to name it. And if you have more than one ligand, like you have cobalt, Cl, Cn, NO2 and NH3, we have taken this example earlier. If you have this, so what you will do, if before this your cationic entity, you write name of the cation, whatever, this is complex entity. If the name of ion is after this, so first you will finish this part, then you write the name of ion. So here it is suppose potassium, right? We to start with potassium. I'm not taking that also. If you have finished this part, then you will come to this part. So you write the name of the ligand. So when you write name of the ligand, so what is noticeable? So when the name, so this will be given as what? Tetraamine. First A, then chloro, then cyano or cyanido, and then nitro. In your book I saw this is given nitrito, so it's a printing mistake. And if you have this and then one sulfate or something, so here it will be sulfate anyway. So this part, if this name and then you will have cobalt, and its oxidation state you can find out X with the charge N or whatever oxidation state. So that is not my aim here. So oxidation state you can find out. I have told you how to calculate. If the charge is no charge, so you will take it 0 here and then you can find out. Okay. So here that is if this name is given, then how you will write this? Okay, if this is given, you don't know, then how you write? You will see here. You will write them what name when we write alphabetically. But then formula when we write, then we start with the ligand when we are in the complex entirety. If the potassium is here, to write K and all whatever. So I am not taking that any part. So here when you are there, so you will start with first anionic ligand. Anionic ligand is this and this. Then you will see their alphabetical order. So this is chloro and then nitro. So you will first and cyanido. So alphabetical order will be what? Chloro, then cyano, and then nitro. Negative ion, and then amine. Amine is neutral. 4. This way. And then we have what? Cobalt. Central metal atom. Central metal atom is always written in the beginning of the square bracket. So you must have seen. So this order I have taught to you in the beginning. When we write the formula, the negative ligand must be written first. Then should be the neutral ligand, and then at last there will be the positive ligand. 2-3 positive ligands are there. Nitrosonium ion, nitronium ion, hydrogenium ion. These all I have given to you earlier. So when you are writing the formula, then ligands you will be writing how? You will be writing the ligands first anionic ligand, and then your neutral ligand, and then positive ligand. If you have more than one negative ligands, then you will see their alphabetical order. So first name, first letter of their name. So that's all, student. And in the next class, I'll teach you isomerism. And in the next class, in the next video, rather in the next video, I will be uploading assignment that will be the question based on ISC question paper. For the last previous year, at least of 10 years, and then you can go through it. So till then, bye, and I hope you are studying properly. Take your time to study, and a lot of exercises are given in the book for writing the name, and so you can take practice. So bye, students.